One more time. All right. Okay, we're on. That's quick, huh? Okay. So, all right. Remember the last time we talked about the beam already, and you were introduced to the plastic capacity of the beam. And before we go into that, let me remind you again that when you are dealing with the beam, it's too nice. The calculation of the nominal moment, you have to consider two things. Okay. Yes, it's true that when designing the beam, you're going to have to consider the shear and some other things, but that will come later. Let's focus on just the flexural aspect of things first, okay? And in considering that, we need to consider the global buckling of the beam. Now, that's a issue where we'll tackle later, but let's say in global buckling, when you say your beam is laterally braced first. When your beam is laterally and properly braced, you will be able to reach what we call MP, or plastic moment, which is what we did last time. We can reach plastic moment, which is defined by the plastic section modulus. Okay, and this is defined by the special stress distribution where all the section yields, and therefore we can calculate the new section modulus that we call plastic section modulus. And that is when your beam can reach its full capacity. Okay, remember that this is the maximum that you can get. The maximum strength, flexural strength that you can get out of the steel beam is plastic moment, if your beam is laterally braced. Okay. The next thing that you need to check is, again, local buckling. In order for your beam to reach MP, you must not have local buckling either. If local buckling occurs, it may prevent your section from reaching MP, of course. So we need to check that. And again, in terms of flexural aspect, there are two things you need to check. But this time, let's assume that your beam is laterally braced, so it could reach MP. However, to guarantee that your beam will be able to reach MP, you need to make sure that both your flange and your web will be strong enough so that your beam can reach MP without the problem of local buckling as well. This time we are going to focus on the local buckling of the flange and the web. Well, it's still the flange and the web, just like the compression member, but the stress is different, and therefore we have a different limit from compression member. Okay, and flange is unstiffened element. If you can recall, it's an unstiffened element. This time we check the ratio, which is BF/2, divided by TF, which is for convenience, we generally write down BF/2TF. It's a ratio of the flange. Okay, this time we have three limits, okay, which you have seen a little bit from last time. Okay, we have three zones. If the slenderness ratio of the flange is less than what we call lambda p, your flange is compact. If the slenderness ratio of the flange exceeds lambda p but not lambda r, we call our flange non-compact. And if it exceeds lambda r, it becomes slender. okay? And you can say the same about the web. The web is the stiffened element. Oh, my handwriting. Okay, here it is. The web is different element. Okay, and you check the H over TW ratio. Remember, the H is the distance between the two fillets. So it is not the depth of your section. Okay. Now, let me tell you right away that right now, okay, listen carefully, the design of the flexural member by AISC, they sort of categorize the web first. You need to always check the web first. Check first. Okay. When your web is compact, the series of the flange will be, in the series of a compact web. That's how they do it. And say if the web is non-compact, when you check the flange, the series will be under the non-compact scenario, non-compact web scenario. When the web is slender, you're gonna check the flange in the slender web scenario. But for hot roll, however, for hot roll, which are the section that you guys use, it's a typical section available in the market. For all the hot roll sections available, all web are compact. Okay, so that means we are going to check the slenderness ratio of the flange under the compact web category. Okay, now this is very important. The AISC will specify the behavior of the beam based on the slenderness ratio of the web. But for the hot roll, we only have compact web hot roll. So whenever you choose to use the hot roll H section, you always have the compact web. And therefore, we have one category to worry about when we check the slenderness ratio of the flange. Now you may ask me if it's possible to have the non-compact web and the slender web. Why do they categorize that if you don't have the non-compact or slender hot roll? The answer is yes, but you will have the slender web when you are using the built-up section. For example, whenever you go out and see the steel bridges, the bridge made of steel beams, those beams webs are always slender because they would want to have the biggest number of moment of inertia as possible. And by wanting that, the best way to do it is to increase the size of the flange. To increase the size of the web will not be very beneficial. It only makes the beam heavier. So they would prefer to make the flange very, very big, but the web not so. So they have the design approach where they can deal with the slender web. And some of you guys may get to do that if you go out and become a bridge engineer, or if you have the opportunity to design a transfer beam, a very big plate girder. You would not want to have the very thick web because when you increase the thickness of the web, the moment of inertia doesn't increase that significantly or beneficially or efficiently, whatever you want to say. So we can have that, but not with the hot roll. And the scope of this class is just for the hot roll section. So you guys can be sure that whenever you use the hot roll web, it is always compact. So when you check the flange local buckling, it will fall into just one category. Okay, but even though you now know that all the webs of the hot roll section available in the market, I am tempted to say anywhere in the world, but I wouldn't go that far, but it may be close enough. Anyway, you should always show in your calculation that you check your web and it is compact. All right. or if you don't want to show it, you must make a statement that according to blah, 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 web is compact. But you cannot say according to me. Okay, I am not a valid reference. You shouldn't do that. Okay, so that's a focus today. So let's go back to the slide. Okay, when we've done that, this is the perspective of the local buckling that I just mentioned. If you know by now, so let's say all the web is compact. So let's focus on the flange. So if you have a compact flange, your beam will be able to reach MP here, right? Your beam could reach MP if all the elements are compact, but now you know web is compact. So if the flanges are compact, both of them are compact, we call that a compact section. I mentioned this the last time, right? And when you have a compact section, your beam should be able to reach MP. But when if either the web or the flange is non-compact, your beam will have local buckling before it reaches MP, and therefore the flexural capacity must be reduced. And further, if either the flange or the web is slender, we are down to a very, very low moment carrying capacity. Okay. And we have mentioned this, that the flange can buckle locally like this under bending moment, and likewise the web. But you just sort of have in mind that for, you can say for hot roll, web is always compact. Okay. Now, we need to have a little bit of a knowledge, because the residual stress is the stress that can reduce the load carrying capacity of your section. But if you get to MP, you know, in the end, we can override the existing residual stress. Pardon me? Somebody's moaning. Is that a question? The screen doing okay? Okay. So if we manage to get to MP, we can override the existence of residual stress. So that means if we have the compact section, we need not worry about the residual stress. But if you are somewhere in between, say when you have non-compact section or cylinder section, the residual stress will come into your consideration. Okay. Now, let's say it doesn't matter whether you have the web or the flange, you know, not compact. So I'm just going to say this in the overall picture. Okay. I have mentioned before that if you check the slenderness ratio and it is lower than the limiting value that we call lambda p, and you can say that I say lambda pf here because, you know, you guys know that only the flange will have the issue. If you have the compact section, that means both the flange and the web are compact, the flexural capacity of your beam is MP, and that means the behavior of the beam is in the plastic region. Okay, if either one of them becomes non-compact, that means the slenderness ratio exceeds lambda p but not lambda r, you will have the non-compact section. One of the elements fall into this category, you have the non-compact section. And you see the load carrying capacity is reduced linearly, and the behavior in this region we call it inelastic behavior. And if either your flange or your web is slender, that means the slenderness ratio exceeds lambda r here, you will have the slender section, and the behavior of your beam becomes elastic behavior according to this line based on the plate behavior. I can tell you that, you know, this behavior is real. You can see it if you have compact section, compact flange, compact web, you can load your beam until it fails because the moment reaches MP. This is real. We have proved that. We have the stress strain relationship to prove that. This is also real based on the plate behavior. If either your flange or your web is slender, it becomes a slender plate and it buckles accordingly. And this is derived from the plate theory. This is also real. However, the one in the middle, the inelastic behavior, it is a sort of, not very clear-cut behavior. So in fact, this is just the line connecting the plastic behavior and the elastic behavior. Okay, but it's there because before the plate becomes truly elastic, there's some room between plastic and elastic. That's why it is there, but the behavior here is just so assumed to be linear, sort of. Okay, so that becomes our design curve if we have either the flange or the web that is not compact, and your moment capacity will be reduced accordingly. Notice that right here, this is MP. But right here, this is not MY. Okay, this is not MY. It's not the first U moment that we use. It is MR. It is MR. It is the moment that is residual stress is deducted. So MR is not Fy multiplied by Sx, just like My. Remember, My is your first yield is Fy multiplied by section modulus, right? But well, let me try to fix this. Okay? It's stress. Okay. Well, when I raise my hand on the iPad monitor, it just so it is as if I raise my hand on. I put my hand on the whiteboard and just it wipes things out. I can't believe it. MR is only 70% of Fy multiplied by elastic section modulus. So 30% is deducted for the effect of the residual stress. Okay, so remember in the consideration we use MR, not MY. And if you ever wonder, this is the reason why we call it lambda R, not lambda Y. Okay, so we have lambda P and lambda R. Okay, so this is the basic concept of the design curve of our beam. Now let's we have mentioned this about the compact section, non-compact, and slender. Okay, so I'll pass that. Here's the limit that we talked about. Lambda P, see, unstiffened element, lambda P. So this is for flexural member. You have either this or that. You can use the channel as well. And remember, this time you have two limits and lambda R. Lambda P is 0.38 square root E over Fy. Lambda R is just square root E over Fy. Okay. The next is the web stiffened element. And there you are. Web of doubly symmetric I shape. So this is, I should have kept the height. Lambda P and then lambda R. For your web. Notice that, please use the H, not the D. Okay, and don't forget to always indicate that you have investigated the slenderness ratio of the web if you don't plan to calculate. Okay, and I don't know, I really don't I'm really not going to say that you're wrong if you don't check lambda r, if you know that your web slenderness ratio is already less than lambda p. Okay, but you just need to make a good clarification. All right. All right. So this is the formula shown in the spec. Okay. If you have the non-compact flange, see, now your web must be compact. When you come to this page, web must be compact already, which we have that. When you have the slenderness ratio of the flange, BF over 2 divided by TF is greater than lambda P of the flange and then not greater than lambda R of the flange. Remember that this is 0.38 square root E over Fi. This is 1. Okay. This will be the moment capacity of your beam. Okay. And if it exceeds lambda R, so your BF over 2 divided by TF is greater than lambda R of the flange, this becomes your capacity. Okay. But I can tell you again that of all the sections available here in Thailand, for hot roll section, you have only non-compact. I have never seen slender flange before. There's no point trying to make the flange slender, right? I have never seen it before, but that doesn't mean that it doesn't exist. But to my knowledge and experience, it doesn't. Okay, but don't be so sure about that. Okay, I can be wrong sometimes. All right, so if I put that into our design philosophy, this will be your one and all graph that you can always use. Okay. This is lambda p, the flange. Lambda p is this value. And for the web, it's that value. Okay. And then lambda r right here. Lambda r for the flange and then lambda r for the web. You can see that need to do this first, right? This is the flange and that is the web. Okay, so if you, as long as you have this page of mind, you should be fine. When both ratios are under lambda p, your nominal moment is equal to mp, which is of course Fy multiplied by plastic section modulus. Now, if let's say the slenderness ratio of the flange exceeds lambda p but not lambda r, your moment capacity will be approximated by this formula. And please notice the formula. This is the linear equation, you know. MP is the beginning value. This is the slope. See, that is basically dy by dx. See, that's the dy, right? MP is the height, and this is your MR, 0.7 FYSX, that's your MR. So this term is this, you see? And then lambda RF minus lambda PF, it's this term. So that's the slope. And then this is just your X value, right? Lambda minus lambda P. So ladies and gentlemen, please look at the formula. If your lambda is less than lambda P, your lambda is of course the slenderness ratio of your element, okay? It's B over T. And for the flange is BF over 2 then divided by TF, right? If your lambda is less than lambda P, you should say right away that your nominal moment is equal to mp, right? But what if you miss the point and you use this formula instead, F3-1 equation? If you use this one instead, the term in the parentheses becomes negative because lambda is less than lambda PF. When this term becomes negative, and negative, it becomes positive. So you would have nominal moment greater than mp. If I see that, I will be very, very upset by your lack of sense of engineers. Okay, so if you investigate your section correctly, you can identify them correctly, that should not be a problem. Okay, and again, let me finish this even though we don't have this, but anyway, if the slenderness ratio exceeds lambda r, your nominal moment can be calculated from this formula. This formula contains a new term called Kc. Kc can be calculated by using this formula. And the spec suggests that if you calculate Kc and it is less than 0.35, use 0.35. We don't go below that. If it is greater than 0.76, use 0.76. We don't go beyond that as well. Okay? Remember that this is flange local buckling, or you can call it FLB. Okay? And if you have the issue with flange local buckling, it means that local buckling may occur before your beam can reach MP. You can simply say that this will become your load carrying capacity because you cannot reach MP. Or you can simply say you check both the global buckling and flange local buckling and pick the lower value. That's it. Okay. So, that's it. Is there any question? If there isn't any question, it's time for us to take a look at our first example. Where? Oh, here. Okay. So the first one is just a simple evaluation of the moment capacity in LRFD. Right? Because it's VMN. So let's use the blue. That's LRFD. And that is ASD for this particular section, H350 by 250 by 69.2 with the SS 400 steel. Okay, you can pick this information from the table. Okay, if you want to open the file, look at the table yourself. That's it. Okay. You know what? Generally, I should give you more tables for flexural members. I will do that later. If I forget, please remind me. It has every calculation for MP and MR and so and so. Okay. But even if you don't have that, it shouldn't be too difficult. Okay. So this evaluation is based on, let's say, the fact that our beam is compact. Okay. No, I mean the beam is, say, laterally braced. So we need to check the compactness of the section. Okay. So you can say we have the flange. For the flange, your lambda F of the flange is 0.38 square root E over Fy. Okay, so that becomes 0.38 square root of say 2.04 multiplied by a million divided by Fy is 2500. Okay, this is equal to 10.8. Okay, so that means you have this equal to 10.4. So lambda flange is equal to 10.4. Is less than 10.8. So you can say you have a compact section. Okay. Next is the web. For web, lambda p of the web, you see the number is pretty large, right? 3.76. It's like almost like 10 times greater than that. You see that? Square root E over Fy. So that's 3.76 square root of 2.04 multiplied by a million divided by Fy, which is 2500. There you have it. 107. See, the lambda P of the web is pretty high. Do you know why? It's because your web has both tensile and compressive stress. So it is very, very difficult to buckle. That's why the limit is so high. So that is why we always have the compact web, because it is very difficult to buckle due to the fact that two kinds of stress exist at the same time. So lambda is 34. It is less than 107. So you have a compact. I should say, excuse me, not compact section. I should say compact here. So we can now conclude that we have a compact section because both the flanges and the web are compact. Okay? So we now can calculate the nominal moment because it now can reach the plastic moment, and nominal moment is equal to Fy multiplied by plastic section modulus here, which is that one. Remember, MP is plastic. So, okay. Oops. Oh, what is this? Huh? No, it wouldn't go. Okay. All right. So it is 1210. Okay. If you don't change the unit, you see that the number is so large, like 3020000 kilogram centimeter, which is an ugly unit, you know. Well, I generally use a ton meter. Okay. So this LRFD, it is VMN, right? So you multiply that by 0.9 and I change the unit. So in the end, turns out to be 27200 kilogram meter and divided by 100. Or ASD, it is nominal moment divided by factor of safety. So I have 18100 kilogram meter. Okay, but that's it. So I can say that if we, have I posted the rubric? Sort of forget, but anyway, I will check today. I owe you guys a lot. So that's the thing. I don't have another example that I should have. So let me try to give you one extra example here, okay? So that you can see how local buckling may affect your moment capacity. So we are going to investigate the H 400 by 200 by 56.6 kilogram per meter. Okay, this guy has and it is SM520. So you see, when I use a stronger material, I will have the lower buckling limit. All right, so that shall be interesting. SX is 1010 centimeter cube. ZX is 1130. The unit is the same. The ratio of the flange BF over 2TF is equal to 9.05 for this. See, the ratio doesn't have unit, okay? And the H over TW is 48.9. Am I going too fast? Because we started a little late, so let me try to finish this example before we have a break, okay? So again, we check the compactness. All right. But this time, I should begin by writing this first. Lambda F is 9.05. We compare this to 0.38 square root E over Fy, which is 0.38. This time, E is the same, 2.04 multiplied by a million, but this is 3700, okay? Because I run out of space. So let me try to increase the size of the square root to cover that. Okay, this is equal to 8.9. You see what happens? Now lambda F exceeds the lambda PF limit. Okay, that's for the flange. All right. For the web, again, you should always check that. Lambda web is 48.9, but you know, because this limit is so high, it is highly unlikely. But again, we should make it complete. So it's 3.76 square root E over Fy. So that's 3.76 square root 2.04 multiplied by a million divided by 3700. Okay, that's 37. Okay, not you guys can see it. Again, this is still pretty high. It's 88.1. So we can say that this is non-compact web, compact flange. So in the end, we have to conclude that this is a non-compact section. And only the flange is non-compact. So this time I am going to calculate the nominal moment based on that formula. So the nominal moment becomes MP minus MP minus MR. I can say MR, you can say 0.7 Fy S X direction. And this is lambda minus lambda p of the flange divided by lambda r of the flange minus lambda p of the flange. Okay, and since we have the momentum in every term, I have to say the term, it's two terms now. So I can sort of bring the Fy out and I can rearrange this as the, plastic section modulus in X minus Zx minus 0.7 Sx lambda minus lambda Pf over lambda Rf minus lambda Pf, and the whole thing can be multiplied by Fy later. Okay, so now we have, oops, my screen sharing is paused. Okay, we're back in business. Okay, so Zx is, excuse me, trying to be consistent. Okay, so Zx is 1130 minus 1130 minus 0.7 multiplied by 1010. Okay, this is 9.05 minus 8.9, that it? Yep. Divided by 23.4 minus the 8.9. I forgot to calculate that for you. So this 23.4 is in fact, because when you have this situation, you should check your lambda RF as well, and I forgot. So my apologies. Let me fill it in here. But for that, let's erase this first. And lambda RF, should put it in here too. Lambda RF is equal to 1, right? 1.0 square root E over Fy. And that is equal to 23.4. So yeah, the ratio is 9.05. It exceeds lambda p, but not lambda r, which is equal to 23.4. Okay, so that's the 23.4 that you may wonder, right? And now we multiply this by Fy. Since I'm running out of space, I'm just going to use like this. And you should know that it's 3700. Okay, so that in the end turns out to be 41.9 multiplied by 10 to the power 5 kilogram centimeter, or 41.9 ton meter. So that's it. After checking the local buckling, this extra example demonstrates that it has a local buckling issue and therefore it will not be able to reach MP. This value after the calculation should be less than MP. Okay, so you should always check the local buckling of your flexural members. Okay, so is there any question? Is there any question? Okay, so let me stop the share and stop the record.